This is our fifth example on torque. So in this problem, a uniform beam of length L and mass 1.8 kilograms is at rest on two scales. A uniform block with mass M equals 2.7 kilograms is at rest on the beam with its center at distance L over 4 from the beam's left end. So the question is, what do the scales read? So following our steps in solving torque-related problems, first we identify what are the forces acting on our object. So our object is the beam. So of course, it has its own weight. Let's call that weight of the center of mass, weight sub cm. And since the block is placed on it, it has the weight of the block. Let's call that weight sub capital M. Now the beam rests on two scales. So meaning to say, the beam is exerting a weight on the two scales. So by Newton's third law, the scales exert an equal amount of force in the opposite direction on the beam. So let's call those two force pairs to be F and R to the, since it's on the right, and F and L since it's on the left. Okay, so these are the only forces acting on the beam. So next, we choose a pivot. So say we first choose to pivot on A. Let's say this is pivot A. Okay, so let's redraw the forces. We have F and R here. We have weight of the block, weight due to the center of mass, and normal force on the right. Let's put the dimensions. This is L over 4. This is L over 2. And the length of the whole beam is L. Okay, so let's set up our equations. So since our object is in rotational equilibrium, sum of torques must be 0 along A. Okay, so what are those torques that sum to 0? So let's look at the forces one by one. So weight sub M. It causes a rotation in its direction. So clockwise, so it will have a negative torque. So we write minus weight sub M times the lever arm of L over 4. So next, for the center of mass, we see that it also provides negative torque. So this is minus W sub cm times L over 2. Lastly, we have this force. So now this force provides a rotation in this direction, which is counterclockwise. So it will be positive. So F and R times its lever arm of L. So from our equations, we can see that we can factor out L's and remove it in our equation. So now we have minus Wm times 1/4 minus Wcm times L over 2, 1 over 2 plus FNR times 1. So solving for FNR, we have the mass of the block is 2.7 kilograms times gravitational acceleration g. So this has negative times 1/4, positive na, positive, plus the mass of the beam is 1.8 kilograms times 9.8 meters per second square times 1/2. So solving for FNR, we have 15.435 newtons. So by Newton's third law, these 15 newtons will be the reading on the scale in the right. Here. This should be L. Okay, so now let's solve for F and L. Okay, so we assign another axis of rotation or pivot here. Let's call that B. Okay, so the torques at B must be 0. So at B we have 0 equals, so let's see the torque contributions one by one. So this is at B. Okay, so let's start by F and L. So this force is causing a torque in this direction. So this is clockwise, this should have negative sign. This will be minus F NL times its moment arm of L. Next, we see that W sub M is causing a rotation in this direction. So this is counterclockwise. So this will be positive. So we would have W M times 3/4 L, which is its moment arm. And then, since W sub m and the center of mass is at the same direction, their torques must be of the same direction. So, W sub cm times 1/2 L. So, again, L cancels out. We can solve for F and L. Okay, so F and L now is 1.8 kilograms times 1/2 plus 2.7 kilograms times G times 3/4. So this will have a value of 28.665 newtons. So the reading on the left would be 28 newtons.